Right. Welcome back. This is Mr. Youngren with our last lesson of not only of quadratics, but the last lesson that we're doing for the entire school year. So congratulations on making it through. Let's make sure that we keep working hard and finish strong and still continue to learn about quadratics. And we're going to actually learn how can we use equations of quadratics to answer some real world problems or some applications. So your standard that you're working on is that I can use my knowledge of quadratics to identify and solve for important information from real world context. Parabolas show up all over the place. The most common thing that you see with applications and the ones that we tend to think about are paths of like a ball or a rocket or some kind of object that gets thrown in the air, right? Because it goes up, it hits a maximum point and then comes right back down. Know that we see quadratic applications all over. There are quadratic equations used to predict different business models, used to predict how to maximize profit. The list goes on and on. So we want to know how can we take an equation and then go ahead and use that equation to help us find different parts of the quadratic and answer some important questions. Now, before we get nervous about the fact that they're word problems, remember what we've done with quadratics. We've focused on a lot of ideas, and one of the main ones is finding x-intercepts, right? The whole reason why we factored was to find x-intercepts. The whole reason why we did the quadratic formula was to find x-intercepts. And when we're working with quadratic applications, guess what one thing we're going to have to do is find x-intercepts. Now, we just have to think about what does that mean in terms of the problem. The other thing that we're going to need to do, and we did this quite a bit, it wasn't in every lesson, but that was to find the vertex. One really unique feature about quadratics is the fact that it does have like a vertex or a maximum or a minimum point. So if you see the word maximum or minimum in any quadratic problem, that's telling you find the vertex. And we know how to do that depending on the form. All right, so let's go through. We're going to just do two examples together. I'm going to show you how these should be pretty straightforward. If we can identify exactly what piece of the quadratic we're looking for, we can then find that very quickly. All right, so the first problem we're going to do is says the graph below shows the height h in feet of a small rocket t seconds after it is launched. The path of the rocket is given by the equation h equals negative 16t squared plus 128t. How long is the rocket in the air? If I just think about this, I might be like, I have no idea. If we have a graph, and one thing we're gonna encourage you to do is to draw a picture, we can start to kind of narrow this down. And so what I always like to think about is, I visualize this in my head, or if I can write it down on paper, I do that. So I'm looking at it, I'm like, okay, here's where the rocket starts. Right, that's at 0 seconds, it has not been launched yet. Over here on the y-axis, that's 0 feet. So it's been launched, it goes up in the air, it's going, and then it turns around at its maximum height and then comes right back down. And so when it comes back down, this is where it started, this is where it hits the ground again. Right, if the feet above the ground is 0, that means it's on the ground. And so if I'm looking at this x-axis, that's the time and the time that it's in the air. So the difference between these two x-intercepts gives me how long it's been in the air. I don't need to solve this. I can clearly see that it's 8 seconds based on the graph. Now, if I wanted to graph it, or if I wanted to find it algebraically, how do I find x-intercepts? Factor, quadratic formula, any of those things. In fact, this is very easily factorable. So let's make sure, one thing we like graphs because we can see that point, but I want to confirm this. So I'm going to actually do this algebraically. So I'm going to factor this. And the very first step in the factoring that we really pushed you to do in this unit was to look for a GCF. Because if you look for a GCF, many times that's all you need to do to factor. So I'm looking at this equation, what do they both have in common? They both have a t, that is for sure. I also think I might be able to pull out a 16 or even a negative 16 from both those numbers. So I'm checking, is 128 divisible by 16? It is, it gives me 8. So what I'm going to do is I'm going to factor this equation to be h equals negative 16 t, sorry, let's try that again. H equals negative 16t, and then times t, and since I divided by a negative 16, 128 divided by negative 16 is negative 8. So minus 8. Remember, I could check this. If I distribute the negative 16t back in, I should have the exact same thing. So if I set these equal to 0, I get negative 16t equals 0, meaning t will be 0. And if I set t minus 8 equals 0, I just need to add 8 to get t by itself. And there we go. There's that 8 that agrees with the graph. And so anytime we're answering an application problem, we're going to give it context. I don't want to just say 8 because it could be 8 minutes. It could be 8 hours. In this case, it's 8 seconds. Right? What is the greatest height the rocket reaches? Again, the picture is very helpful. Like, what's the highest point? Right there. And what do we call that in terms of the parabola or the quadratic graph? It's vertex. So that's what we need to find. What is the vertex, and how can we go ahead and find that? So if I'm looking at the graph, it looks like the vertex is just above 250, where each of these lines, it looks like it goes 10, 20, 30, 40, 50. So I'm guessing 260. Now, I can look at the graph, I can assume it's 260, or we can find it by finding the vertex. So let's actually go ahead and find the vertex. So x equals negative b over 2a, or negative 128 over negative 16 times 2, which is negative 128 divided by negative 32. I get 4. That makes sense, right? Halfway in between 0 and 8 is where it reaches this max height, so 4. But that's just the time it takes to reach its max height. Its actual maximum height comes from us plugging this back in. So I'm going to say h equals negative 16, 4 squared, plus 128 times 4. And I'm actually just going to plug all that in my calculator. So negative 16, I'm going to put 4 in parentheses, square it, and then plus 128, and then times 4 in parentheses as well. And press enter, and it tells me 256, which is different than what we thought, right? If I were to just assume what it was on the graph, I would have called it 260. But it's actually 256. But once again, let's make sure we're checking our units. It says height in feet in the actual problem itself, but also on the graph, I can see the feet right there. It's 256 feet. So good thing we solved for that. Okay, the graph is nice, but really, we don't assume anything. We want to make sure that it is completely correct. All right, number C, or letter C, excuse me. How high is the rocket after 1 second? Well, we can just, all that means is that t equals 1. I can look at the graph to get an idea. If I follow 1 up, it looks about 100 feet. Let's make sure of that. So I'm going to find what happens when I plug in 1 for t into the equation. Once again, I'm just going to use the calculator. These numbers are fairly large. I don't expect any of you to do this in your head. So negative 16, 1 squared. I already know that's going to equal 1. Then 128 times 1. Oops. Let's try that again. Negative 16, 1 squared plus 128 times 1. You get 112. And again, the graph showed me something different. It was close, but I would have just said 110 feet, not 112 feet. All right, now the next questions actually are asking us to use the graph. So it says about how high is the rocket after 2 seconds? We can find where it's 2. We can trace this up. I see this point right there. Each line here is 10. So it's 10 less than 200, so about 190. And in math, we can do this squiggly sign. That represents about equal to or approximately. So about 190 feet. And then at 2 seconds, is the rocket going up or down? This is talking about its path, right? So if we look at where the rocket started, it's still moving up and up and up at 2 seconds. So we'd say at 2 seconds, it's still going up because it has not reached its max yet. Our next question, using the graph, answer the following about how high is the rocket after 6 seconds. So same idea. I'm going to find 6. I'm going to trace it up. And it looks like we're actually at the same place as we were for 2 seconds. And so I'm going to say at about 190 feet. Then at 6 seconds, is the rocket going up or down? Well, at this point, it's already hit its maximum, right? It was going up until it hits its highest point, and now it's starting to head back towards the ground. And so this one, it is going down. And it says, use the equation to find the exact value of the height the rocket at 2 seconds. We've done this. It just means plug in 2 to the equation. We should expect it to be somewhere close to 190. So 128 times 2. Again, I'm going to use my calculator. So negative 16, 2 squared plus 128 times 2. We get 192, which is really close to our guess based on the graph. But this is exact, so we'd say 192 feet. All right, and that's it. All right, so that's really all that we're having to do. Find X-intercepts or find the max value or plug-in values. Okay, we don't need to overthink these. If we have the equation, it's just a matter of what exactly do we need about that graph. All right, let's do one more together, and then that'll wrap up all your videos for Algebra 1. So this time it says a ball is thrown in the air. The path of the ball is represented by the equation h equals negative t squared plus 8t, with h as the height in meters and t is the time in seconds. That's just like what we saw before. Graph the equation on the graph below. So we're going to start with that. So I'm looking at this when I go ahead and graph. There's a bunch of ways that we can go about doing this. The best way that we know how is if we have the vertex to then go ahead and use our a value. Let's do that now, and then we can also figure out our scale. So I'm going to figure out, and I know there's not a ton of room here. Let's actually use this space up here. I'm going to figure out what is our x-coordinate of the vertex, so negative b over 2a is negative 8 over 2 times negative 1. So negative 8 divided by negative 2 is 4. If I plug 4 in, we have h equals negative 4 squared plus 8 times 4, and that equals, let's just use a calculator, 4 squared plus 8 times 4, 16. And so I have a vertex at 4, 16. So I'm going to go ahead and plot that. And then I can clearly see that my a value is negative 1. So I then can use all those rules that we have of the a value to go from one point to the next. So vertex is right 1, 2, 3, 4, and up 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And now using my a value, it tells me, since it's negative 1, to go down 1 and over 1. Then I need to multiply the a value by 3, so tell me to go down 3 from there. 1, 2, 3, and over 1 again. And then after that, we multiply our a value by 5, so now tell me to go down 5 and over 1. 1, 2, 3, 4, 5. And then from there, it'd be times 7. So I now want to go down negative 1 times 7, which is negative 7 and over 1. 1, 2, 3, 4, 5, 6, 7 over 1. 7 over 1. And there we go. So it's nice when the graph is exact like what we have here. But even if we just do a rough sketch, that sketch itself can help us figure out what part of the graph do we need to answer the question. So now, what is the maximum height of the ball? Well, here's what's nice. We already found that, right? The max height is talking about the vertex, right? It's going to hit its highest point and come back down. So its height is the y-coordinate, which we found to be 16 meters, which is a fairly good throw, 16 meters. How long does it take for the ball to reach the ground? Well, think about how we did it last time. Or let's think about what do we got going on here? Well, right there at 0, 0, that's where the ball is being thrown. So that's where it starts from. And then once it gets back to 0 feet, this is where it hits the ground. So how long it's in the air for, right, it's going up and back down, is all this amount of time that's passed. I can find that point, right? That was one that I plotted as whole numbers. So I don't even need to solve for that. I can just see it's 1, 2, 3, 4, 5, 6, 7, and 8. 8 seconds. Kind of like the rocket. 8 seconds for the ball to be in there, that's a heck of a throw. Right, use the equation to find the exact value of the height of the ball after 3 seconds. Just like we did before, we're just going to plug in 3, and then that is it. Negative 3 squared plus 8 times 3. So negative 9 plus 24, which is 15. So you'd say 15 meters. Does that make sense? Should it be about 15? Yes, right? It's really close to reaching its max height, so 15 does make sense. All right, that is all that I have for you today. Thanks for watching all the videos. Thanks for all your hard work. Make sure you complete your video check-in. Have a great rest of your day and a great rest of your semester.